It's a great pleasure to introduce our first keynote speaker, Edward Lee. Edward studies cyber-physical systems that integrate physical dynamics with software and networks. Edward has, as most of you probably know, done contributions in terms of models of computations with time and concurrency, model-based design and analysis, domain-specific languages, architectures for real-time computing, schedulability analysis, programming of distributed real-time systems, and so on. Many of these ideas are embedded in the Ptolemy platform that I guess those working in the area of cyber-physical systems will be aware of. Edward now is a professor for EECS at the University of Berkeley, where he also heads the Center for Hybrid and Embedded Software Systems. Edward has been at Berkeley since 1986 on the faculty. He has a bachelor's from Yale, a master's degree from MIT, and a PhD from Berkeley. Edward is the co-founder of BDTI, where he now serves as a senior technical advisor. Edward then is a fellow of the IEEE, prefers to be called Edward rather than Ed, in order not to be taken for the mayor of San Francisco, whose name happens to be Ed Lee. And he's going to talk about models in science and engineering, specifically the role and future of deterministic models. It's a great pleasure to have you, Ed.
Thank you very much, Alexander. I really appreciate that introduction. I'm really thrilled to be here. I am honored to be invited to give a keynote at Models. I actually have given a keynote at Models before, 6 years ago at Models in 2010 in Oslo, which is 1,500 kilometers from here, as you can see on that map. It's particularly gratifying to get invited again. Most conferences that invite me for keynotes never want to see me again. And you may feel the same way after my talk today. I hope not. But I did go back and look at the presentation that I gave at Models in 2010, and I was very tempted actually to just give the same talk again. I could almost have gotten away with it. This is actually a slide from that talk. At that time I introduced a brand new modeling language that I called TUML, the Truly Unified Modeling Language. And as you can see on the slide, it's a very formal language. In fact, the entire specification of the language is in this mathematical expression right here. So a model in TUML is a function that maps a rectangular region into 0 or 1. And when you render it visually, you just put a dark dot wherever it maps to 1 and leave a white dot wherever it maps to 0. So here's an example of a TUML model. And it's, in fact, if you just add a profile and then every existing UML notation is a special case of one of these models. So anyway, this language didn't catch on at all, or actually maybe it did. Maybe it's the most commonly used modeling language today, I'm not sure. But in any case, I decided that it would be better to give a completely different talk today and not repeat the talk from then, because this kind of statement can really get me into trouble in this crowd. So just some context. So I work in cyber-physical systems, and that's a particularly challenging problem area for the topic of my talk today, which is determinism. And I guess I'm a bit of a masochist. I pick very difficult combinations of things to talk about. And I'm going to try to convince you today of the value of deterministic models, even for systems like cyber-physical systems that have a lot of intrinsic dynamics, a lot of unpredictability, a lot of uncertainty about the environment. And on top of that, they're safety-critical systems. So you're sort of faced with the situation where you have all this uncertainty, but you still need to somehow build certainty and build confidence in these systems. And so my question that I'd like to address is really, does it make sense to talk about deterministic models for such systems? Now, I'm going to take a very broad view of what a model is, and it may be broader than you're comfortable with initially, but hopefully bear with me because I think there really is some validity in this. So here's an example of a simple model of a physical system. This happens to be a model that describes Newton's second law, which is F equals ma. So it describes the motion of a body as a position as a function of time, the velocity as a function of time, and force on the body as a function of time. And there's a modeling framework associated with this, which is the calculus of Newton and Leibniz, and the framework of Newton's laws. So Newton defined the notion of force, for example. And that can be used to describe some physical system like this one in the lower part of this image. My claim, and the big picture claim that I'd like to hopefully this will be a takeaway from this talk, is that a lot of people, engineers in particular, confuse the model with its target. They think they're talking about the model, but they're actually talking about the thing being modeled, or they think they're talking about the thing being modeled, but they're actually talking about the model. So one of my favorite ways of expressing this confusion comes from Solomon Wolf-Golomb, who said, "You will never strike oil by drilling through the map." And he's emphasizing the importance of understanding the distinction between the map, which describes a territory, and the territory itself. And I would also like to emphasize that in no way does this diminish the value of a map. It's just that you have to understand the different role that it plays in whatever you're trying to accomplish. Now, okay, determinacy. So my claim is that some of the most valuable models are deterministic. What do I mean by deterministic? Well, in the context of models, it's actually reasonably straightforward to define what deterministic is. So I'll just take this as a definition. A model is deterministic if given the initial state and given the inputs, the model defines exactly one behavior. Now, that may seem like a simple definition, but it's not as simple as it looks, because the terms that are in italics here have to be defined more precisely. So what is the state of a system, for example? You have to define what that is before you can really have a clear notion of what determinism is. What are the inputs to the system, and what is the behavior of the system? These things have to be nailed down before you can really talk about whether a model is deterministic. But once you nail them down, the definition becomes unambiguous, and that's a pretty valuable property. Now, in the title of my talk, I talk about Laplace's demon, and so Pierre-Simon Laplace was actually born only 170 kilometers from here in Normandy, so right around here, and around the turn of the 19th century, Laplace postulated, he was sort of building on the tremendous enthusiasm and the tremendous success of Newton's models of the physical world, because these models were very usefully predictive, and you could use them to really understand dynamics of systems in ways that before Newton were really just speculation. And so, Laplace, caught up with the enthusiasm about these models, postulated that if you had what he called a vast intellect, and this later became known as his demon, and if this demon was able to know the position and momentum of all of the particles in the universe, then the entire future of the universe could be determined by that demon from those initial positions and momentums of those particles, using Newton's laws, in effect. Now, this idea of the physical world being deterministic has proven to be a really problematic issue. Certainly in physics, there's a very strong commitment to deterministic models. It would seem that in the 20th century that this idea of deterministic models kind of fell apart with quantum mechanics, but apparently the contemporary view among physicists is that it didn't actually fall apart. It's just that it changed what we had to define as the state of a system. So for example, in quantum mechanics, it no longer becomes possible to deterministically know position and momentum of an object simultaneously, which would suggest that there's some intrinsic non-determinism in the system, and in fact quantum mechanics models position and momentum using probability density functions. But actually, if you view the state of the system as being its wave equation instead, then quantum mechanics once again becomes completely deterministic. So this is a quote from Stephen Hawking, who describes this as basically science snatching victory from the jaws of defeat by moving the goalposts and redefining what is meant by complete knowledge of the universe. So this is really just redefining the notion of state. And if you redefine the notion of state, quantum mechanics gives you a deterministic model of the universe. So this keeps Laplace's demon alive. In principle, it should be possible to think of the world, the universe, from a physical perspective as being deterministic, and the possibility of being able to do prediction in the form of Laplace's demon. So in 2008, this fellow, David Wolpert, who was then at NASA but is now at the Santa Fe Institute, published a paper where he proved that Laplace's demon could not be realized in the physical world. And his essential argument was that in order to realize Laplace's demon had to exist within the physical world, the very physical world that it was predicting. And this self-referentiality yielded an incompleteness, not unlike Turing's incompleteness and Gödel's incompleteness, which are also both due to the ability to have self-referential models. And so in some sense, you can see this as saying, well, okay, this demon can't possibly exist. So does that, in fact, undermine this idea that the physical world is deterministic? Or does it just say that it is deterministic, but we can't actually use determinism for prediction? Or what does it say? And this leads to a vast amount of confusion. Add to that a lot of confusion that arises when you talk about the physical world being deterministic and you start to ponder whether we have free will, etc. And it becomes a really muddy mess, this whole notion of determinism. So I think that in a way, as engineers, our problem is much easier than the physicists. And the way that I approach this problem is based on an idea that I first learned from Hermann Kopetz. I actually learned this sitting at a breakfast table with him in Vienna before a conference. I was thoroughly jet-lagged. I came down to breakfast. The place was really crowded. There was no place to sit. I recognized Hermann, asked him if I could join him. And we got into a conversation, and he told me, he made a statement something like this, where he said, many properties that we assert about systems, like determinism, timeliness, reliability, etc., are in fact not properties of the system, but rather properties of a model of the system. And I took that away, and it really changed my thinking about a lot of things. One immediate consequence of this is that if you accept this, it makes no sense to talk about whether the physical world is deterministic. That's actually it becomes a nonsensical question. You can't actually really say anything definitive about the physical world at all. You can only say definitive things about models of the physical world. And if those models are deterministic, and you can show unambiguously that they're deterministic, then the question changes to one of whether the model is useful rather than to whether the model is true. So this issue of whether a model is useful versus whether a model is true I think is a really important part of not confusing the map with the territory. What we want are models that are useful. The truth value of these models, I think, is almost irrelevant. And consequently, I'd like to just completely put aside the question of whether the physical world is deterministic, and for cyber-physical systems, address the question of whether deterministic models are useful for cyber-physical systems. Okay, so my claim is that determinism is a property of models and not a property of the systems that they model. And consequently, we have to view it from that perspective. So let's look at cyber-physical systems. So here's a pretty typical schematic of a simple cyber-physical system. Every cyber-physical system has some physical dynamics. It's driven by actuators that are controlled by computers. It has sensors that feed data into computers, and typically there are multiple computers communicating over a network. So think of, for example, of a factory automation scenario. That's a fairly typical cyber-physical system application. if we want to decide what kind of models to use for this sort of system, as good learned engineers, the first thing we should do is, of course, look at what are the most successful models from both the cyber side and the physical side. So we've got kind of three different worlds here. We got the networking people and their whole culture. They use modeling quite a lot in networking. We have the software world, and we have the physical world of mechanical engineers, chemical engineers, civil engineers, etc. And all of those worlds have their own modeling techniques, and they have a very rich tradition of modeling techniques. So let's start with the software side, the cyber side of cyber physical systems. So my claim is that software is in fact a model, all right? Here's a physical realization. The physical realization is actually electrons sloshing around in silicon, and the software is a model of some behavior, okay? So here's an example of a C program that, if you make certain assumptions about well-behavedness, has exactly the properties of determinism in that it has well-defined inputs. This function has input argument that is typed precisely enough to know exactly what the inputs are, and it specifies exactly one behavior. And if you look carefully at this program, you can determine that definitively line 8 in this program does not execute. Okay, so you can do static analysis and come to a very definitive conclusion, in large part because this is a deterministic model of a behavior. The target, of course, is electrons sloshing around in silicon. The target takes time, consumes energy, it fails if you drop it in the ocean, and none of these are properties of the model. So the fact that the actual implementation has properties that are not properties of the model shows you definitively that this is in fact a model. It is not an implementation, as some people might claim. And in fact, this becomes particularly important in a minute with cyber physical systems to recognize that a piece of software is not in fact an implementation of a system at all. Now, software relies, in fact, on another deterministic model that abstracts the hardware. So the fact that that C program is not what gets executed directly, it gets compiled into a machine code that is defined according to an instruction set architecture. So the idea of an instruction set architecture was introduced by Fred Brooks way back in the 1960s when he was at IBM. And it's largely, actually, the concept of instruction set architectures really has changed remarkably little since the 1960s. It is a deterministic abstraction of the behaviors of a family of machines, and it is a deterministic model of what the silicon does, okay? Now, the instruction set architecture is based on yet another deterministic model that underlies that, which is the model of synchronous digital logic. So this wafer shows each of these die, or do you call them dice in the plural? Dies or dice? I'm not sure. But in any case, this is about a little less than 2 centimeters squared. It's a quad-core Intel processor with a GPU on it, and there are 1.4 billion transistors on each of these dies. Okay, 1.4 billion transistors. You cannot design something with 1.4 billion individually controllable parts without using deterministic models. Trust me, you just can't do it. And the fact that synchronous digital logic exists and provides a deterministic model makes it possible, in fact, for the silicon designers to construct these very complicated designs entirely within the world of modeling. They're not doing bench test prototyping. They tape this thing out, and with very high probability, it works exactly as specified the first time it's manufactured. That's a remarkable feat, and to me, it's a real testament to the value of models, but it's also a real testament to the value of deterministic models, because the fact that the synchronous digital logic model is a deterministic model, I think, underlies our ability to be able to create these incredibly complex designs. So I've given you a stack of 3 models on the cyber side, all of which rely very heavily on determinism for their effectiveness. Synchronous digital logic, instruction set architectures, and single-threaded imperative programs. In fact, I would argue that the determinism of those three models underlies the information technology revolution. That without that determinism, we wouldn't be where we are with the information technology revolution. So let's turn our side to the physical side of cyber-physical systems. So on the physical side, there's a longer tradition of using deterministic models among mechanical engineers, civil engineers, etc. So I mentioned earlier Newton's laws. This is simply Newton's second law expressed again. And mechanical engineers use these differential equations all the time to describe the behavior of physical systems and to design these systems. And they design them quite reliably. The fact that airplanes, fly with confidence these days depends a lot on the determinism of these differential equation models. In fact, interestingly, the engineers that do this even use these deterministic models to analyze these systems for tolerances to variability in manufacturing, for margins of stability. So if they get perturbations, unknown perturbations, for example, you can analyze margins of stability for a system. So you're actually using determinism in these models to analyze their behavior under unknowns, which is, perhaps a little surprising, but actually it's a very powerful use of deterministic models to be able to use them for analysis like that. Now, one of the interesting characteristics of these models that are used on the physical side of cyber-physical systems is that when they talk about dynamics, they're talking about the evolution of the state of a system in time. On the cyber side, once you get above the synchronous digital logic level, we throw out time. We throw it out completely, okay? And as a consequence, we create an enormous problem for cyber-physical systems, which is that if you take a deterministic model from the cyber side using the state-of-the-art techniques and you combine it with a deterministic model from the physical side and you construct a model that describes the interaction between these two, that combined model is always non-deterministic today, always. And that's because the cyber side doesn't say anything about time. It simply doesn't say anything about time. The fact is that correct execution of a program in all widely used programming languages and correct delivery of a network message in all general purpose networks has nothing to do with how long it takes to do anything. And when you combine that with the physical world, which cares a lot about when things happen, the result is that you don't have a model that describes one behavior. You have a model that describes many possible behaviors, all of which fit within the model, and consequently you have a non-deterministic model. Now, of course, programmers do design real-time software, but they have to step outside the programming abstractions to specify timing behavior. So in effect, they're working without a map. So this has fairly profound consequences. So a story that I heard first from an engineer who had worked on the Boeing 777. So the Boeing 777 was Boeing's first fly-by-wire aircraft. So a fly-by-wire aircraft means that computers mediate the pilot commands, and they communicate over networks to actuators in the wings and so on to control the flaps, okay? Now, the 777 started flying in 1995, and this engineer from Boeing told me that Boeing expected to be making this plane for about 50 years. That's a typical production run for a commercial aircraft, okay? They're making them now, they're selling very well. But what he told me really shocked me, which was that he told me that Boeing purchased the complete stockpile of microprocessors that they expect to use for the entire 50-year production run of the plane, and another 50 years of maintenance on this plane. So a 777 rolling off the production line in the year 2035 will use microprocessors that were made in the early 1990s for its flight control system. Why? Because the behavior of the software system is not specified by the software. The software interacts with the physical world. Correct execution of the software is certainly possible with modern microprocessors. I could drop in a modern microprocessor, run the same C code for that flight control system, it will correctly execute that C code with very high confidence, and the behavior will be different. This is proof, by the way, that that C code is not an implementation. It's a model, and it has left out critical information about the behavior that you actually care about, because you care about the interaction between that software and the physical dynamics of the system. Now, I subsequently talked to people at Airbus who have been making fly-by-wire aircraft for longer. The A320 was their first fly-by-wire aircraft, and they tell me they're really nervous about, whether the shelf life of the microprocessors that they buy today is sufficient for the production run of an aircraft. They store their microprocessors in liquid nitrogen to try to slow down the natural diffusion processes in the silicon so that they have a hope of extending the shelf life. Now, to me, this is a profound embarrassment to the world of computer science, because in effect we have not given these engineers effective models to build software and to build something that would be correct. Now, one way to think about this is that, we have these wonderful abstraction layers that we work with. Down at the lowest level, we have microprocessors. Then we have instruction set architectures, a great idea due to Fred Brooks. Then we have, bytecode interpreters, another great idea. Then we have programming languages and so forth on up the stack. And the purpose of each of these abstraction layers is to hide the details of the implementation below and provide a platform for designing from above. So that, for example, the writer of a Java program doesn't have to worry about exactly which microprocessor they're working on. Now, the fact is that for the aircraft designers, every one of these abstraction layers has failed. They're stuck with their design actually being the implementation. Any model that they have is useless. What really describes the implementation is the silicon and wires, and that's it. Okay, so we need to solve this problem somehow. Now, the question this brings me back to the question of determinism. We failed to provide determinism by combining the best of class deterministic models from the cyber side with the best of class deterministic models from the physical side. Does it really make any sense to talk about deterministic models? So here's where maybe the main takeaway from this talk should be, right? What is the value of models? Well, in science, the value of a model lies in how well its behavior matches that of some physical system. That's why scientists use models. They use them to describe physical systems, and the model is good if it describes the physical system well. But in engineering, we do something a little different. In engineering, the value of a physical system lies in how well its behavior matches that of a model. If I give you a piece of silicon that doesn't behave like that synchronous digital logic model, that piece of silicon is not worth anything to me. There's nothing wrong with the model. It's the piece of silicon that is flawed, right? That's a very different use of models than the scientific use of models. These are very complementary uses of models, and I think both scientists and engineers will use models both ways. But these are different uses of models. So in engineering, model fidelity is a two-way street. So it's incumbent on the physical system to match the model as much as it is on the model to match the physical system. Whereas in science, it's much more one way. It's incumbent on the model to match the physical system, and we don't hold the physical system responsible for failing to match the model. But in engineering, we do. So, of course, for a model to be useful, it is necessary to be able to construct a faithful physical realization. So here's a model of Newton's cradle. You can tell it's a model because it's too perfect, right? It's a simulation with beautifully rendered graphics, beautiful shading, shadows, and so forth, lighting. It's sitting right on top of a copy of Newton's Principia Mathematica. Beautiful model, too perfect. Here's a physical realization that I bought on Amazon for $6, including shipping, and it's a piece of junk, right? I mean, look at this thing. The balls in the middle are supposed to stay still, and it's not even close, okay? Now, to a scientist, the model is flawed. To an engineer, the realization is flawed. And I'm an engineer. I hold that realization responsible for being a piece of crap, okay? I don't think there's really anything wrong with the model. So in view of that, what's the role of deterministic models for cyber-physical systems? I think if we change the question, the role becomes much clearer. So I believe the question is not whether deterministic models can describe the behavior of cyber-physical systems with high fidelity. I think that's the wrong question. That would be the scientific question, but we're not doing science, we're doing engineering. So the question should be, can we build cyber-physical systems whose behavior matches that of a deterministic model with high probability? And I am absolutely convinced that the answer to this is yes, we can. Okay? We just have to develop the right tools. So, really, determinism? What about resilience, adaptability? The environment's going to throw Murphy's Law at us right and left. Everything's going to go wrong in the field, right? So why don't we just acknowledge that and give up on determinism and work with non-deterministic models and say, you know, everything just has to be resilient and adaptive. Well, of course, Murphy's Law doesn't go away. Deterministic models do not eliminate the need for robust, fault-tolerant designs. In fact, my claim is they enable robust, fault-tolerant designs, because deterministic models make it very clear what it means to have a fault. So if you have a deterministic model of a system, you have a very systematic way to detect when a fault has occurred. Faults will occur no matter what your model is, right? Even single-threaded imperative program can have an alpha particle flip a bit. It can have the chip overheat. The circuit board could get dropped in the ocean. Be careful with your cell phones when you go out, you know, wading in the tide pools here. There's all kinds of things that can happen in the physical realization. That's true. If you have a system that defines very clearly what a correct behavior is, you have a mechanism for detecting faults, and therefore you can design systems that are tolerant to faults. So determinism and fault tolerance and resilience are not at all at odds. In fact, they're very much complementary. Now, we have done a number of projects at Berkeley that have been focused on addressing this question of how to build useful deterministic models for cyber-physical systems. And I'll point you to two of them that both ended last year, ended successfully in my view as far as academic projects are concerned, which means we published lots of PhD theses and lots of papers and produced some open source software, but unsuccessful in the sense that the uptake in industry has been rather slow. We're starting to see some impact from the second one, but the first one the uptake's been a little slow. But together these two projects, they give a programming model for distributed concurrent real-time systems where the programming model is deterministic in the same sense as single-threaded imperative programs. And I want you to just pause on that a little bit, because a lot of people think concurrent means non-deterministic, okay? It doesn't. Concurrent can be perfectly deterministic in the same sense as single-threaded imperative programs. But together these models also add to that determinism of single-threaded imperative programs deterministic timing with respect to the external interactions. And both of these are very practical, very realizable models. Now, I could spend my remaining time giving you the technical details of these, but I'm not going to do that. I'm going to let you look them up if you're interested, and I'm going to instead contradict myself, okay? I believe in yin and yang. Everything positive has a corresponding negative. Everything white has a corresponding black. In this image, that's what these mean. Determinism has its limits. So it's not a panacea, okay? And we need to understand the limits in order to know how to use it effectively. So what are those limits? Well, complexity is one of them. So here's a picture of a prototype of the Airbus A350. This is Airbus's most recent fly-by-wire commercial aircraft, okay? Believe it or not, this is an entire A350, except that it's missing the airframe, the skin, and the engines, but it has everything else. Okay, it even has the generators that are driven by the engine, so you can, they have kind of an artificial engine that will turn these generators. They power up this system. It has all of the hydraulics of the plane in it. They call it their Iron Wing prototype. It has every wire in an A350 is there at the same length that it is in the A350. Every hydraulic pipe has the bends as if it were going around the airframe, but there's no airframe there. Okay, they call that an Iron Wing prototype. It's a model. It's not the kind of models that we hear talk about much in the models conference. In fact, I think most of us in this conference would find the fact that this model is the best available model a little embarrassing, right? I mean, we'd rather there were a virtual prototype that could be used, but the reality is, no, this is a really incredibly complicated system, and our virtual prototyping technology is really not good enough yet to build confidence in a system like this. So some systems that we have are simply too complex, and deterministic models become they become just intractable as the complexity grows. Another example where that arises is in systems that have large numbers of simple behaviors, like, for example, deep neural networks, or in fact generally machine learning algorithms. These are deterministic algorithms, actually, in the sense that they, you know, if you know what the inputs are, they give you exactly one behavior, but it's very difficult to predict what those behaviors are. And there's an emergent complexity in these systems that makes the use of deterministic models for these systems somewhat less useful than it might otherwise be. And so non-deterministic abstractions become useful in this case. What about uncertainty? The fact is, we can't construct deterministic models of what we don't know. It's, that's a very straightforward thing, and you can't possibly know everything about a system. You can't know everything about its operating environment, and so non-deterministic models become useful, and if we are dealing with known unknowns, meaning things that we know that we don't know, we might be able to quantify our lack of knowledge using Bayesian probability. Interestingly enough, the notion of Bayesian probability, which is distinct from the notion of the frequentist notion of probability, is actually due to Laplace, who was apparently hedging his bets about his deterministic demon, right? Because he was recognizing, in fact, that we couldn't know everything, and therefore using probabilistic models of the physical world was actually pretty useful. And he developed most of the machinery around Bayesian statistics and Bayesian probability at the time. Chaos also arises in deterministic models. So Edward Lorenz was a meteorologist working at MIT in the 1950s, and was one of the first pioneers in the late 50s and early 60s of using computer-based models for weather prediction. And they had actually very, very good deterministic models of the thermodynamic behavior of weather systems, but he found that these models had an extreme sensitivity to initial conditions. And in fact, he determined that the very best of class weather models that they had were unable to predict fine-grained behaviors like formation of clouds and rain and wind and so forth beyond about 7 days. And the reason that he identified was that an arbitrarily small perturbation in the initial conditions would have arbitrarily big effects in the future in these models. So even though the models were deterministic, they were not usefully predictive because they were so sensitive to the initial conditions that any prediction that you would make would actually be undermined by your errors in your knowledge of the initial conditions. So he illustrated that with a simple nonlinear differential equation here, which has characteristic behavior. This is a phase plot of the behavior of two of the three variables in there. And the fact is that the position of a point in the future is not usefully predicted by the model. You really can't, there's no mechanism for determining where it's going to be in the future that is in any way reliable. And this is despite the fact that it's a deterministic model. Now, just recently in 2015, Lothar Thiele at ETH in Switzerland and his team published a really nice paper where they showed that chaos arises in real-time systems in practice with absolutely commonly used scheduling policies that are used for real-time systems. And this is a plot from their paper of the response time of a bunch of tasks under a real-time scheduler, and you can see at a glance that this exhibits chaotic behavior, and consequently the behavior of these real-time systems is not usefully predictable, even though it's actually completely deterministic. Now, the last topic is one where I'll really be sticking my neck out because this is actually unpublished so far. I have a paper that's been reviewed and accepted, and in the usual fashion for journal papers, it takes years before it comes out. In fact, the journal hasn't even appeared on the market. There's a new ACM Transactions on Cyber-Physical Systems, and the first issue has not appeared yet. But in any case, I have a paper accepted that will appear called Fundamental Limits of Cyber-Physical System Modeling. And one of the claims in this paper is that any set of deterministic models that is rich enough to encompass Newton's laws plus discrete transitions is incomplete. So in other words, anything rich enough to do cyber-physical systems, because we need Newton's laws to get the dynamics of the continuous world, and we need discrete transitions to get the dynamics of the cyber world. Anything rich enough to do cyber-physical systems, if it is deterministic, is incomplete. What do I mean by incomplete? Well, let me illustrate this with a very simple example. This is a completely physical system that mixes discrete and continuous behavior. So imagine that you've got two billiard balls on a frictionless surface. And one of the balls is approaching the other, and this one's sitting still. Then when this red ball collides with the blue ball, you expect something to happen. That collision we can model as a discrete event, okay? And if the masses of the balls are the same, the red ball will simply stop and the blue ball will acquire its momentum and start rolling to the right, okay? If you've ever played billiards, you're familiar with that behavior. So how would you predict this behavior with a model? Well, according to Newton's laws, there's really two constraints that need to be satisfied by this system, which is because there's no mechanisms for loss of energy in this system, we have a frictionless surface and we have ideally elastic balls, then we need to satisfy conservation of momentum and conservation of kinetic energy, meaning that the momentum and energy in the system should be the same after the collision as it was before the collision. That's the only requirement imposed by Newton's laws, and it's sufficient to derive, in fact, the rest of Newton's laws when you use these conservation laws. Okay, so you can write this down, write down these conservation law equations, and then you can derive the solution for this two-ball problem. And it turns out, because energy is a quadratic function of the velocity, there are two solutions, not just one. The first solution is that the velocities of the balls after the collision is the same as it was before the collision. That obviously conserves both energy and momentum, but it has a little physical problem because it means that the red ball tunnels right through the blue ball. Okay, the blue ball remains still and the red ball just keeps moving right through it. So let's rule out that solution because it seems nonsensical, okay? And we're assuming these aren't, these are macro scale particles, they're not quantum scale particles, so we're not going to allow for tunneling. So we just rule this out, and then we're only left with one solution. And once we've ruled that out, we have a deterministic model. A very straightforward deterministic model. We can derive the velocities of the balls after the collision as a function of their velocities and masses before the collision. And here are the formulas. So this is the velocity of ball 1 after the collision, and it's a function of the velocity of ball 1 before the collision, the velocity of ball 2 before the collision, and the masses of the two balls, m1 and m2. Okay? So it's a fairly general set of formulas and a completely deterministic model. Now, let's change the problem slightly, and let's assume that we have three balls. Also, everything's still in one dimension. So you have a billiard ball sitting still in the middle, and you've got two balls approaching it at equal velocity from opposite sides. So they're going to come and they're going to collide with that ball in the middle. Now, hopefully your intuition is the same as mine, which is that they would just bounce. If all the masses are the same, the balls will bounce away, and they'll just move, the two outer balls will move away at equal velocity, right? Seems like a reasonable prediction. So the question is, can we derive that prediction from Newton's laws? Well, it turns out that we have a mechanism here for dealing with a single collision between two balls, but this mechanism doesn't actually work once you have two simultaneous collisions. Because if you have two simultaneous collisions, we will still have two equations, the conservation of momentum and conservation of kinetic energy, but now we have three variables. Okay, and so it turns out that there will be more than two possible solutions in general. Okay, so one way to handle this is to reduce it to individual collisions. So we can say, all right, at the time of the simultaneous collision, let's just ignore one of the collisions temporarily and handle the other. Okay, so we have a two-ball collision between the red and the blue ball, and assuming that the masses are the same, this will simply result in the blue ball acquiring the momentum that the red ball had. Okay, so the red ball has stopped, and the blue ball is now moving towards the yellow ball with the momentum that the red ball had initially. Now, key to this is we do not let time elapse. Without time elapsing, we now have a new collision here. Again, it's a two-ball collision, and consequently the behavior is deterministic. We can handle it deterministically and determine that the two balls will move away at equal velocity. Okay? And then once we've handled that, we get a third collision, which we can handle, which is that the blue ball is colliding with the red ball, which is stationary, and the end result is that these two balls will move away at equal velocity. Seems to work, okay? In fact, it works fine even if you reverse the order and you handle the right collision and ignore the left first, okay? You get the same result either way, but only if the masses of the balls are the same. It turns out if the masses of the balls are different, you get a different result depending on which collision you handle first. That's weird, okay? You get a different result, and moreover, both results are asymmetric. Neither result is the one that we intuitively thought, which is that the two balls would move away at equal velocity. In fact, both of the results that occur from handling the collisions one at a time in this deterministic fashion are asymmetric. So here's a plot of the positions of two balls constructed from a simulation depending on which collision you handle first. Okay. So this is a problem. So we don't actually have a deterministic mechanism for determining the behavior of this system. Maybe the problem is ill-posed, right? So recall the Heisenberg uncertainty principle, which says we cannot simultaneously know the position and momentum of an object with arbitrary precision, but to talk about these collisions as being simultaneous collisions, we have to know position and momentum to arbitrary precision. Otherwise, we can't even talk about this problem. So the Heisenberg uncertainty principle kind of suggests that our problem here is ill-posed, and we shouldn't be talking about these collisions being simultaneous. Okay, so let's not talk about them being simultaneous. Let's assume that there's some time difference between the collisions. They're slightly off from being simultaneous, and let tau be the time difference between the collisions, okay? Then it turns out that you can construct a sequence of deterministic models. For any tau that is non-zero, the model will be completely deterministic. Whether tau is positive or negative, for any tau, the model is completely deterministic, okay? You can construct a sequence of models as tau approaches zero. That sequence is demonstrably a Cauchy sequence, meaning that the behaviors of the models are getting closer and closer and closer together to one another as tau is approaching zero. But in the limit, this sequence of deterministic models is not deterministic. So you have, in fact, a space of deterministic models that is incomplete in a metric space sense, meaning that there are holes in this space. If you have this space of deterministic models, there are always going to be holes in that space where no deterministic model will work. Okay? And this is for any modeling paradigm that is rich enough to do cyber-physical systems. In a paper in 2014, which I published in IEEE Access, which basically means it gets reviewed in 1 month and published immediately, instead of reviewed in a year and published 2 years later, as most journals are. But anyway, in this IEEE Access paper, I show that any direct description of this scenario actually results in a non-constructive model. So this is, I don't know, some of you might be familiar with the constructive semantics that Gerard Barry, I think, really nailed down with synchronous languages. So it turns out that the limiting case of these models results in non-constructive behavior, okay? And the only way to resolve that non-constructive behavior is by making these models non-deterministic. Okay, so constructiveness and determinism seem to be integrally tied according to this result. Okay, you could say, well, all right, your basic problem is that you shouldn't have modeled the collisions of balls as being discrete. I mean, the cyber world loves to model things as being discrete because that's all of our, basically everything in the cyber world is discrete, right? So I kind of like discrete models because I like the cyber world, but the physicists could say, well, no, wait a minute, you know, the balls when they collide, they don't actually, it's not a discrete collision. They're actually, you know, when they get close enough, the molecules in one ball will start to become entangled with the molecules in the other, and the balls will maybe compress a little bit, and the kinetic energy will get converted to potential energy because of the compression, and then you decompress. Okay, fine. So let's just construct a deterministic model by modeling the balls as springs. Turns out that doesn't solve the problem, because if you model the balls as springs, stiff springs, you get chaotic behavior. So here's a plot of the positions of the balls with ever so slightly varying initial conditions, and you can see that the final behavior is really quite different. The entire set of initial conditions is not even visibly different here, and it's radically different in the end. Okay? So if you model this as a deterministic continuous system, you get chaotic behavior. Moreover, the space of deterministic models here is still incomplete because as the spring stiffness goes to infinity, the model again becomes non-deterministic in the limit. So you still get incompleteness of the space of deterministic models. In that paper, I also showed that if you reject discreteness, you also have to reject the notion of causality. It's impossible to reject discreteness without also rejecting causality. So the consequences of rejecting discreteness are really pretty drastic. They undermine a lot of the way that we do modeling. And I'm not going to give you the details of that, but the example that is given in this 2014 paper it's a very common circuit example called a flyback diode circuit that is used routinely whenever you have an electrical circuit driving a motor. So it's a very commonly used circuit, and the circuit has a very interesting property, which is that when you open the switch for driving the motor, the causality of the components in the systems reverses. Okay, so with the switch closed, you have A causing B. With the switch open, you have B causing A. And I don't know of any mechanism to move from a situation where A causes B to a situation where B causes A. If you don't do that discretely, you have to pass through a non-constructive phase where you've given up on causality, where neither is causing the other, okay? So there's pretty drastic consequences to giving up discreteness, so I don't think that's the right answer either. Okay, so I've given a pretty complicated, multifaceted story here. I apologize for that, but let me try to summarize it for you. So the first thing I said is that deterministic models are extremely useful. I think they underlie, in fact, the information technology revolution, and on the physical side, they underlie the industrial revolution, okay? If we take our best-of-class deterministic cyber models and we combine them with our best-of-class physical models today, deterministic physical models, the result is always non-deterministic models. And to me, that is unfortunate because we lose a lot of the value of those deterministic models. We know we have existence proofs that we can build deterministic models with faithful implementations for cyber-physical systems. We have to change some of the models on the cyber side primarily in order to embrace time. Okay? Time has to become part of the model once again in order to be able to do this. Then I switched to the yin side of the yin and yang story and said, well, okay, deterministic models aren't always possible or practical because of complexity, unknowns, chaos, and incompleteness. So my end conclusion is that determinism is a really powerful tool. You should use it if you can. The value is enormous. Back off only when you can't. And you will face that. There will be situations where determinism won't work for you anymore, and at that point, then you can justify using non-deterministic models, but not before. So in conclusion, models play a central role in reasoning about and designing engineering systems, and determinism is a valuable and subtle property of models. And I have a book written for a general audience that'll be coming out next year that addresses these modeling questions from a fairly high and fairly philosophical level, and I hope you will find it interesting if and when it finally comes out with the slow publication processes that are involved. Thank you very much.
Thanks a lot, Edward. Can you hear me? Yeah. Thanks a lot. Wow. We do have time for a few questions.
Okay, thank you first for this very good talk, nice talk. My name is Gregor Engels, I'm from Germany, and thanks to CPS, we have a lot of work in Germany in Industry 4.0. And we have learned that there are also humans involved when we speak about cyber-physical systems. And now we speak about cyber-physical social systems. I'm wondering what happens in this case when we have to model humans. Do you think that the model of a human should be part of a model, or is it outside of the model? And does it stay then? Yeah, I think then we also speak about non-determinism when we speak about humans.
Yeah, that's a very good question. I confess that I don't actually understand humans, and so I wouldn't have any idea how to construct deterministic models of them. But I do want to point out one thing, that when we talk about deterministic models, the deterministic models that are most interesting are ones that have inputs from the environment, and you get to define what you mean by inputs, right? And if your inputs are very free-ranging, right, then you can define, your deterministic models give the behavior over all of the possible inputs. So in effect, even with deterministic models, you can talk about their behavior under a non-deterministic environment because it describes a behavior over all possible inputs. So if you really can't say anything at all about the humans, then their effect on the system should simply be modeled as inputs to the system. Personally, I think that we can probably do better than that by actually constructing some models of the humans. There are certain limitations. For example, even a wildly frenetic little kid can only push a button so many times per second, right? And so we could construct models that talk about, circumscribed possible behaviors from the humans. And I have a colleague actually at Berkeley who's been working on this problem, and she has a very interesting formulation where she's very interested in how the automata in an automaton-human partnership, how the automaton affects the behavior of the human. Okay? Often we think of it as the other way around, but actually her take is that no, actually these interactions are very much closed-loop systems, and there's bidirectional effects, and so she's doing very interesting work in that area, but that's really a little bit beyond my expertise, because as I said, I don't understand humans.
I'd like to follow up on that question for a second, and that is the role between environment models and system models. Now, of course, what is a system? I now assume that there is that distinction somehow. And when you were giving your argument about non-deterministic behavior being a consequence of combining two models, you were combining a model of the system, which was the code, with a model of the environment, which was the plant, whatever kind of system you fed there. And then you dropped that distinction somehow. Why is that? And I guess Gregor's question is talking about environment models here, and you were taking that up.
Yeah, that's a very good observation. So I want to emphasize that when I combine these two models, I was combining two worlds where we actually do know how to construct very good deterministic models of those two worlds. Right? If you think of a factory automation system, barring human interaction, right? If it's a fully automated factory, we know how to construct deterministic models for every piece of that system, and they're very useful deterministic models. We can't combine them, however. So that's a problem that I think is solvable. Once you put humans in the loop, well, that becomes more of an open-ended research question, I think, because that's a bit more challenging.
Yes, but maybe it's also a consequence of what you said in the second part of your talk, that environment models should be non-deterministic and system models should be deterministic.
But what is the environment? You're right. I mean, the environment is whatever I, as an engineer working on a piece of the problem, I'm not responsible for, right? So, you know, where do you draw the boundaries? That becomes the question.
Electrical engineers do that all the time, though, right?
Yeah. I mean, if you think about, for example, a very, very current problem is self-driving cars, right? And so, you know, a lot of the open loop approach is that you sense pedestrians and you avoid them. A better approach, perhaps, is to understand how the motion of a car actually affects the behavior of pedestrians, because it does. Okay, every driver knows that. You interact with a pedestrian who is maybe thinking about stepping into the crosswalk, but maybe doesn't step into the crosswalk because you don't slow down or something, right? You understand that interaction as a human, and if we can design the systems to also understand that interaction, they'll probably perform better than if they're just running open loop.
More questions?
Hi. I'm Andy Shomaji. I work on modeling language.
Please put the microphone to your mouth.
Hi. I'm Andy Shomaji. I work on designing modeling languages to describe biological systems, and I noticed your original two-body problem, that has an analytic solution, so we can actually perfectly solve this, but the second one, that's a three-body problem which does not have an analytic solution, which means it has to be numerically solved, so you'll always end up with a sensitive dependence on initial conditions.
I don't think this has to do with it being analytic. In fact, in the three-body problem, if I construct a continuous model based on the stiff spring model of the balls, everything is analytic actually in that formulation. You can derive the solutions in closed form for any particular initial conditions, but you still have that very strong sensitivity to initial conditions, so you have chaotic behavior.
Mm-hmm. Yeah, but what I was saying is, when we have a two-body problem, we can actually solve it in closed form without having to numerically integrate anything. But in a three-body problem, we fundamentally have to have a numerically integrated.
Oh, actually, I don't agree with that. If we model the collisions as discrete, we do not have to numerically integrate anything.
As discrete, yeah.
Yeah, but my claim is that we get essentially the same behaviors as we do if we model it as a continuous system.
Yeah.
And so, the model that models the collisions as discrete is much simpler than the model that models the collisions as continuous.
Mm-hmm.
I'm Taylor Riche from National Instruments. So cyber-physical systems are very interesting to us, and you mentioned time as the one thing that are not currently in the cyber side. Are there other constructs that you feel could help the cyber side sort of join with the physical side better and produce a better end product?
Yeah, that's a good question. By the way, we work quite a bit with National Instruments. You guys have a lab in Berkeley that they've hired several of my students. That's a good question. Yes, there are, of course, many other aspects to a system that can be of interest that are not expressed in the software. I personally don't like the term non-functional properties, which a lot of people use for lumping all those aspects together. So often when I talk about, the temporal behavior of software, people will immediately say, oh yeah, that's a non-functional aspect, kind of like its energy consumption and its weight and all that. I think lumping all those together doesn't make sense. Time is a very, very fundamental concept in systems, and it's not the same as energy, and it's not the same as weight. They're really quite different concepts. I think there's lots of aspects that need to be taken into account in cyber-physical system designs, but I guess I've focused here primarily on dynamics, which really encompasses the logical behavior together with its temporal behavior.
Waris Harawi from University of Montreal. I want to comment about the statement that in science the conformance between model and system is one way, and in engineering it both ways. I would say in science we consider that the system is here, exists before the model, and the model is a way to understand it or deal with it or somehow. But in engineering, the model could have different functionalities or roles with respect to the system. And in some of these roles, we will have the science perspective. For example, if you want to model a system, so the system could interact with another system. So we cannot change the system, and we cannot have this both directions. Can you comment on that?
Yeah, you're absolutely right, and I alluded to that when I said that both scientists and engineers will use models both ways. Engineers will often use models in the scientific way, and it is certainly useful to do that. But what I'm emphasizing is that there are two distinct uses of models, and just as it's important to understand the distinction between whether you're talking about the model or the thing being modeled, it's also useful to talk about what role the model is playing. And those are two very different roles.
Very interesting talk. I apologize that I might have a little trouble asking this question because I just started thinking about it, but I think there's a general point in it, going back to your example with the balls. In your example, you said with 3 balls, you only have 2 constraints, which is the momentum constraint and the energy constraint. But you really do have a third constraint that was implicit, which is that they interact at a certain point in time. So in terms of differential equations, you don't have an initial condition, you have a condition at some time. They're all in the same position, which is an additional constraint that isn't taken into account in the momentum and energy representation of the problem. And you may deal with this in some of your more detailed analyses, and I'm looking forward to trying to look up your papers. The general point that comes out of this, and the reason I thought it might be worth asking the question, is that sometimes whether or not a model is useful also depends on is it the correct representation of the problem. Even though physically the momentum and energy representation seems to be equivalent, it has certain assumptions and may hide those assumptions and hide the additional constraints that can allow the solution to the problem. And I wonder if that is a point that's behind the example that you gave.
Well, I think you raise an excellent question, and to be very honest, in this result on the incompleteness of determinism, I feel like I've really stuck my neck out, and I could be wrong. Someone might find a fatal flaw in my argument, and it really surprised me when I derived this argument. The idea that determinism was incomplete was sort of unacceptable to me initially, and I could be wrong, and maybe one of you will find the flaw in my argument. I don't think that this third constraint of setting the time of the collision to be simultaneous is going to solve that problem, though. I'm pretty sure that that won't be the flaw, but there might still be a flaw lurking in there, but I don't know what it is.
Hi, Edward. Jim Coplain. Thank you very much. You did make me think, and it's a great follow-up to our discussions of the past evening. There is one thing that came to mind, and that is back, certainly in the 60s and maybe in the 50s, programmers at our former mutual employer at AT&T, viewed programming more or less just as a way of manipulating the flip-flops and the gates and the hardware. And there was this dance of synchronization in time between the way the software modeled the world out there, and the view was main is out there, right? And I'm just the subroutine responding to those. And I think there was a good understanding of time in the software. And we saw this in classical digital switching, you know, for years and years. It seems to have eroded. And so what you seem to be talking about is a prognostication or a hope for the future that we finally will get time back into our software, whereas I'm seeing it moving in the other direction. So do you have any, I mean, we're both kind of the same generation. Do you have any perspective or insight? Why are we where we are? Why have we lost this notion of time? And it shows up in lots of ways. I mean, the Lisp people essentially turned time into space by unrolling things in functional programming. We've lost that. That's very out of fashion. It just seems like time has become a second-class citizen. What's going on?
Yeah, I mean, that's a very good question. And you know, the question you're asking is really a question about culture, I think, more than about technology. And that's a fascinating topic. My sense is that the world of computing went through an absolutely explosive growth in capability for information processing. And our ability to use computers to, you know, do things like search and index and banking transactions and, you know, things that surround us all the time that are basically information processing functions have been the driving factor behind computing for the last 40 years. And I think that the cyber-physical systems world is actually not that new. In fact, I was working on embedded software design in 1978. Okay, I was writing assembly code for 8086 microcontrollers, and I was counting assembly language cycles in order to insert no-ops so that I could, you know, use a GPIO pin to open a switch at a particular time. You can't do that anymore with microprocessors. You can't count assembly language instructions because it doesn't tell you anything at all about timing. But those cyber-physical system applications, even though they've been around for quite a long time, have really been, I think, relatively small in the overall marketplace of computing. Not in numbers, right? I mean, way back in the year 2000, DARPA published something that showed that, in fact, 98% of the computers that were manufactured in the year 1999 went into embedded systems. 98% went into embedded systems. But they were mostly $1 parts, right? And they were not really the visible things that were having the huge economic impact. I think that's changing now. When, you know, as soon as we're starting to see the whole automotive industry change over to compute-intensive operations, we start to see a huge shift in the economic value, which is why I think that this is starting to come to the fore now and didn't earlier.
Maybe we have time for one last question. Then I would like to ask one last question, and that is concerning causality, which is something you touched upon at the very end. Now, if you talk about some physical laws, like Ohm's law, I don't know how that is called in English, where you relate current and resistance and the other things, there is no inherent causality in that law, and yet it's extremely useful to do things constructively. Isn't it okay sometimes to just drop that idea of causality?
That's a very good question, but actually we don't know how to drop it, okay? In every solution mechanism that we have for a causal system requires first reducing them to causal constructive systems. Everyone, I mean, even the, you know, state-of-the-art languages like Modelica, the first thing that they do is they, you know, behind the scenes convert it to a constructive causal model, and then they can solve it. Before that, they can't actually solve it. And so I think it's a very good question. I don't really have a good answer for it, except that we don't know how to handle it in its full generality.
Well, thank you very much, Edward. That was a very exciting talk, and thanks for you attending.